Can you see the screen?
Yes, sir.
Yeah.
So in the last class, we had done till this hydrogen spectrum, where I had given you the Rydberg equation and I had told you that you need to remember it. So today we are going to develop on that only. We are going to see numericals and how to apply this equation. This topic will be like very important. Let's the Rydberg equation we have written. Now let's see how to apply this. Now see, whenever an electron is getting excited at this remember, electron absorbs energy. What will it do? It will absorb energy and go to a higher energy level. When it is jumping from one level to another. Or if it gives out energy, if it emits energy, then also it will jump back from a higher level to a lower level. So if it absorb energy, then it will go from low to high level. And if it is emitting energy, then the electron will return back from a higher level to a lower. So this is essentially what happens when an electron is absorbing or emitting energy. So now there are various energy levels, and you need to know these energy levels. Let's draw the energy level of a beam. This is your n is equal to 1. So this is the first energy level. This first energy level. This is n is equal to 2. N is equal to 3. N equal to 4. N equal to 5. N equal to 6. Like this way it is going. N is equal to 7. Like this way it will go up to infinity. This is your n is equal to infinity. So these are the various energy levels that. So now, if the transition of electron is happening to number 1 level, that means either the transition is from like suppose 2 to 1 or 3 to 1, 4 to 1, anything from wherever it may start, but ultimately it has to reach 1. So we can even start it from infinity. Infinity to 1 can be one transition. And this transition is known as the Lyman's. The Lyman's. If the transition is from any energy level to energy level 1, ultimately it has to reach to the first energy level from any other energy level. Then it is known as the Lyman sequence. Okay. But if the transition is till energy level 2, from anywhere it starts, it doesn't matter. 3 to 2, 4 to 2, 5 to 2, like this is from anywhere it can come, but it comes till level 2, infinity to 2. Then this series is called Balmer series. Balmer series. It is happening from n is equal to till 3, n equal to 3, from anywhere, that doesn't matter. also. Then it is called the Paschen series. Paschen, Paschen series. If the electron comes from anywhere, n is equal to 4. From any other energy level, the fourth energy level, then it is called the brackets. Then if the electron is jumping from anywhere till energy level 5, then it is your fund series, where the P is silent, theta silent, fund series. You not pronounce the P in your pronunciation, the P is silent. And if the electron finally jumps to the sixth energy, jumping to the sixth energy, from anywhere it can start, then it is called the Humphrey series. Humphrey. So as you can see, there can be plenty of transition is possible. Plenty of electron transition is possible. And it is not possible to remember the wavelength of every transition. And moreover, different elements have different wavelengths. So it is not possible to mark up the wavelength. So in order to predict what the wavelength of these transitions are going to be, in order to do that, we use the Rydberg equation. Using the Rydberg equation, we can actually calculate the wavelength of this transition of Rydberg equation. The names of the series are very, very important. You need to know. Now let us make a table form and write down the name of all the series. So that means we'll make a table with the columns being series name. This is your series name. N1, N2. N1 and N2 is of like the Republican, the repercussion, the spectral region. If the series name is Lyman series, the first series is our Lyman series. Lyman series. What happens for Lyman series? For Lyman series, the value of N1 is going to be 1. From wherever it comes, ultimately it will come to 1 only. That is why N1 is 1. And N2 can be 2, 4, till infinity. It can be anything from 2, 3, 4, and the value of N1 is 1. And the wavelength of this transition will come under the UV region. To the wavelength, you will see that the wavelength of this transition will come under UV region. Then the next series is Balmer series. Balmer series. Here the value of n1 is equal to 2 because ultimately it is ending at 2 only and it can start from anywhere. So that's why n2 can be 3, 4, 5, dot, dot, dot. And this transition will fall in the visible region. That means you can actually observe this transition with your naked eye, the visible transition. And the wavelength of this transition will fall in the region of 4000 to 7000. So if you measure the wavelength of this transition, it will come in the data of 4000 to 7000 angstrom. After your Balmer series, you have Paschen series. Ending at 3, starting from 4, 5, 6, anything. This will fall in the infrared region. Then you have your bracket series. Till 4, n1 is equal to 4, can be from 5, 6, 7, dot, dot, dot. Then you have your fun, which over here, n1 is equal to 5, and n2 is going to be 6, 7, 8. Fun is in the far infrared. And how big? Okay, so we have written this in a table-like form. Lyman means n1 is 1, n2 can be anything from 2 to infinity, which is falls in the UV region. Balmer transition is n2 is equal n1 is equal to 2, and the value of n2 can be anything from 3 to infinity, and this falls in the visible region. Or you can also call this as optical transition. Optical transition, optical region. The Paschen means n1 is equal to 3, n2 is equal to 4, 5, 6, like this way. So these are basically the 6 series that you have: Lyman, Balmer, Paschen, Bracket, Fun, Humpty. So now let us see numericals. Because the numericals, what we are going to come in the examination. For example, the numerical is like this. Calculate the wavelength of radiation. Calculate the wavelength of radiation in Lyman series. Lyman series. When an electron, when an electron falls from fourth stationary orbit, fourth stationary state the hydrogen atom. It says calculate the wavelength of radiation in the Lyman series when an electron falls from the fourth stationary state of the hydrogen atom. So how to do this? See what are the information that is provided in this numeric. So the first information that is given is Lyman series. This is the first information. It is Lyman series. And what is given? Then also you are given it is in the fourth stationary orbit. This data is also given here. And what data is given? It is hydrogen atom. So now let's see. Hydrogen atom means what? Z equal to 1 because the atomic number of hydrogen is 1. Atomic number Z is equal to 1. Now see it is saying Lyman series. For Lyman series, what is the value of N1? What is the value of N1 for the Lyman series?
1.
1. So that means over here N1 is going to be 1. Now what will be the value of N2? It says
4.
fourth stationary orbit. That means over here N2 is going to be 4. And what is the value of Rydberg constant? This we are told only. This is 1.1 into 10 to the power of 7 per meter. The values. And you will get your answer. So 1 by lambda is equal to 1.1. So let me write down the formula for it. The formula was Rz square 1 by N1 square minus 1 by N2 square. Just put down the values. 1.1 10 to the power of 7 into 1 is 1 by 1 is square minus of 1 by 4 whole square. That is equal to 1.1 10 to the power of 7 15 by. So if you find out lambda from here by doing the necessary calculus, lambda equal to 9.69 10 to the power of minus 8. The answer of the numerical. So is the numerical clear to everyone? So that's why you need to know the table. The table is very important thing. And then just put down the values of N1 and N2. Once you can identify the value of N1 and N2, then to just simply putting in the equation getting done. So is the numerical clear to both of you?
Yes, sir.
Yes, sir.
Then let's see the next numerical. So the next numerical says calculate the wavelength for the beta line in Paschen series. Obviously for hydrogen. So now let us see what data are given over here. So that one data is given that it is for hydrogen atom. Since it is for hydrogen, that means over here Z is equal to 1. This data is given. And what data is given? It is told that it is Paschen series. Paschen series is given. So Paschen means what? N1 is equal to 3. So by telling Paschen series, basically they have told us the value of N1. Now you cannot see the value of N2 over here. N2 you cannot see. But they have called something as beta line. So which we actually do not know at this moment. What is this beta line? So over here you see, if we consider the transition for Paschen series, what is it going to be? Suppose this is one. These are the energy level. This is a rough diagram. So suppose this is N is equal to 3. This is N is equal to 4. N equal to 5. N equal to 6. Like this way the energy levels are there. So the transition can be 4 to 2 or 5 to 3, 6 to 3. Like this way it can happen. Different transition. 7 to 3, 8 to 3. So now over here, the first line, that is 4 to 3, this is called the alpha line. The second line is called the beta line. Third line is called the gamma line. Then delta line, like this. So now we get to know what the beta line is. So over here, the beta line is going to be 5 to 3, this transition. 5 to 3 is our beta line. So that means N2 is now equal to 5. Okay. Now we can simply do the sum. Is the beta line concept clear to you? Do you now understand what beta line is meant?
Yes, sir.
Okay, then
Yes, sir.
actually, then tell me, suppose for the bracket series, what is the gamma line going to be? What is the gamma line for the bracket series? What is the gamma line for the bracket series? Then
7.
gamma line for the bracket series is 7. Yes, 7 to 4. Okay. So the 7 to 4 transition is basically the gamma line of our bracket series. So now simply putting the formula 1 by lambda is equal to 1.1 So yeah, so if you do the calculation, the answer will come at around 12.78 10 to the power of minus meter. 12.78 10 to the power of minus 7. Okay, so is this sum clear to both of you? Is the numericals
Yes,
being
sir.
clear to both of you? Okay. So then let's move to the next one, next sum. We'll be doing different types of numericals that can actually come from this topic. So the first one was the most simplest, and then we got a bit of variation where it said beta line. Now suppose what if they give us this? Calculate the shortest, longest way, shortest and longest wavelength. of the Balmer cities. For hydrogen. Can you tell me what the value of N1 and N2 is going to be in this case?
N1, 2.
N1 to 2 because it is Balmer cities. But what will N2 be?
Infinity.
Sir, 3.
N2 3, okay. For which one? Shortest or longest? So let's do this. Suppose, so what data are given over here? So it is said Balmer cities. This is already told. And hydrogen is told. And no such data is given. So that means Z is equal to 1. N1 is equal to 2 because it is Balmer cities. Now suppose you take the value of N2 as 3 and calculate the wavelength. What will be the value of wavelength? N2 is 3. 1 by lambda is equal to R. No need to put down the value of R also over here. We're doing a rough calculation. R into Z square, that is 1 square, into 1 by 2 square minus 1 by 3. So this will come out as 5 by 36. That is equal to 5R by 36. So lambda is equal to 36 by 5R. What you get over here? Then you see suppose we take N1 is equal to 2, N2 is equal to 4. That means the next transition. So we did it calculated it for transition 3 check 2. Now we will do it from 4 to 2. So now 1 by lambda equal to R. Z square to hydrogen answer. So no need to do that. 1 by 2 squares minus 1 by 4 square. That is equal to R into 16. 8 minus 4. That is equal to 4 by 16. 1 by 4. So lambda now is equal to 4 by R. 4 by R. So as you can see over here, that the factor 36 by 5R, 36 by 5R, this value is larger than 4 by R. If you do 36 by 5R and 4 by R, you will see that this value will be larger. Ignore the R, ignore, suppose you do not even consider the R. Then what will this come? This is equal to 36 by 5 is equal to somewhere around 7 point something, 7.2, 7.2, and this is equal to 4. 7.2 by R, and this is equal to 4 by R. So naturally, as you can see, that this value is larger. This value of wavelength is larger. Again, suppose if you do it for N1 is equal to 2, but now the transition is N2 equal to 5. That means 5 to 2 we are doing. Now we are considering the gamma line. We have done the alpha and the beta line. Now we are doing the gamma line. So what will lambda be? 1 by lambda equal to r into 1 by 2r square minus 1 by 5r square. That is equal to r into 50. 4 and 25 is LCM will be 50. LCM will not be 50. LCM is rather going to be 100. 100. 25 minus 4. So that is equal to 21. 21. So that means lambda equal to 100 by 21. That means if you take this 100 by 21 is equal to what? It's going to be even more smaller. As you can see over here, that this value gradually goes on becoming smaller as we move to different transitions. So that's why the shortest wavelength will be for n1 is equal to 2, n2 is equal to infinity. N2 is equal to infinity is giving us the shortest wavelength, and longest wavelength money it is going to be n1 is equal to 2 and n2 is equal to 3. Now let's calculate it. So for any series, be it Lyman series or bracket, whatever series be given, there for calculating the shortest wavelength means that series till infinity transition. And longest means the alpha line, the immediately next one. The alpha line is the longest. So this is for the longest transition. So for okay, or for let's do the shortest one. Shortest wave. Shortest wave. So Z is equal to 1. N1 is equal to Bama manager 2. N2 is equal to infinity. So for shortest wavelength, this value should be infinity. Infinity to 2 for shortest wavelength. So 1 by lambda is equal to R. R is what? 1.1 into 10 to the power of 7 into Z square 1s square into 1 by 2 square minus 1 by infinity square. Now what is infinity square? Infinity square is infinity only. And 1 by infinity is equal to basically 0. That's why this becomes 1.1 10 to the power of 7, 1.1 into 10 to the power of 7 into 1 by 4, 1 by 4. So therefore, lambda equal to 4 by 1.1 10 to the power of 7. If we do the calculation, it will come at around 3.6 into 10 to the power of minus 3.6 into 10 to the power of minus 7 meter. So this is the wavelength for the shortest wavelength. Shortest wave. What about for the longest one? For the longest wavelength, Z is equal to 1, N1 is equal to 2, and N2 is equal to 3. So 1 by lambda equal to 1 by minus 1 by 3s. That is equal to, do the calculation of, okay, get it as 5 by 36. So lambda will come at around 12.78, 12.78 into 10 to the power of minus 7 . This is the longest wave. So whatever transition they might give in exam, always remember, for finding the longest wavelength, you have to take the immediately next value, immediately next one. That will give you the longest wavelength. That means N2 and 3, 2 to 3. That means for longest wavelength, always consider the alpha line of that particular transition. And for finding the shortest wavelength, you have to do the infinity transition for that. Okay. So now tell me, suppose, what if now you tell me what will be the transition? Just no need to tell the value, just tell me the transition for the shortest and longest wavelength of Paschen series. The shortest and longest wavelength of Paschen series.
Shortest will be N1 equals to 3
Hmm.
and N2 equals to infinity.
Yes, and longest?
N1 equals to 3 and N2 equals to 4.
Yes. So whatever, not necessarily Balmer will only be given. Whatever series they give, longest wavelength means alpha line, and shortest wavelength means the infinity transition. Let's write it down. Right. Or let's write it in the next page. For finding shortest wavelength, or let's write the longest one before. For finding longest wavelength of any series, consider the alpha line. And for finding shortest wavelength of any series, consider the infinity transition. So is it completely clear to both of you? Yes or no?
Yes, sir.
Yes, sir.
So this type of shortest and longest wavelength question can come. And in this question also, instead of telling Balmer series in the question, they can also give you the optical transition or visible spectrum. Instead of directly telling you Balmer series, they can say calculate the shortest wavelength for the visible spectrum of hydrogen or for the optical spectrum of hydrogen. Now, since Balmer is the only one which is in the visible region. So that is why if such words like visible spectrum or optical transition is being said, that means they are referring to the Balmer series only, because it is only the Balmer series which is visible. So they can give the question in that way. So these questions can be framed in various ways, but ultimately the formula is only one formula is only there. That is red bar. Whatever question might be given, it will be done by the same formula only. So let's take out another sum. This will also be of a different time. Suppose now it says what optical transition? What, how is the weather at your place in Andamans?
Sir, it is ready, sir.
Raining, na? Yeah,
Yes,
because
sir.
there is a
Heavy
cyclone.
rain.
Heavy
Yes.
rainfall. Yes,
Yes,
because
sir.
there's a cyclone forecast in our area. Let's see when the cyclone comes here. We formed today. What optical transition in the spectrum of helium plus. But optical transition in the spectrum of helium plus will have the same wavelength as the fast Lyman transition. Of hydrogen. So try this one out. Try this. Try this somehow. And by the way, see over here. See, we did alpha line. So alpha line can also be called as the first line. This is the first line. Beta line is our second line. Gamma line is the third line. So various names can be given. Okay, so this sum you try. I'll be giving you 2 minutes time. Let's see whether you can do it or not. Are you trying?
Yes, sir.
You get?
Sir, one answer came. Uh, Lambda equals to 1.2 into 10 to the power minus 7 meter.
Okay. But here you do not need to find out the lambda. Okay, see for more further 1 minute. Here there will be easy calculation. No need to even put down the values of Rydberg equation constant. Rydberg constant's value no need to be put in. Okay, so let's see. So here basically you have two sums. See, one is this part. What optical spectrum of helium plus? This is one part. Okay, so let's write for helium plus or HE. What is the value of N1? Sorry, Z first let us write. Atomic number for helium is 2. So Z is equal to. Now it says optical transition. Optical transition means N1 is equal to 2. And they are asking what? Which one? That means I do not know the value of N. N2 is something that I do not know. And that is what I need to find out about it. And now there is second part. Same wavelength as the fast Lyman transition of hydrogen. Fast Lyman transition of hydrogen. That means, but before that, let's frame the equation. So 1 by lambda is equal to R into Z square. What is Z over here for helium plus? Square whole square into 1 by square minus 1 by N2 square. Value of N2 I do not know. So I cannot put the value. And for the sake of simplicity, and for better representation, I will keep it as lambda of helium. So that's why subscript indicates that this is the wavelength for the helium. So that we do not confuse it. Now let's see for hydrogen. For H. For H, Z is equal to 1. That is given. N1 is equal to 1 because it is Lyman transition. Lyman transition is given. N1 is also 1. And N2 is going to be 2 because it says fast Lyman transition. That means the first line they are speaking of. So N2 is equal to 2. Now calculate the lambda for hydrogen. So 1 by lambda of hydrogen, that is the wavelength of hydrogen, that is equal to R into 1 square 1 by 1 square 1 square minus 1 by 2 square. That is basically equal to r into 1 into 4. So that is equal to 3r by 4. 3r by 4. R by 4. So now what does the question say? The question says, you see, that they have same wavelength. The wavelength is same. In both the case, the wavelength is going to be same. So according to question, you can say, according to problem or according to question, whatever you say, according to problem, lambda of Ag plus is equal to the lambda of hydrogen. This is what the question has told us, that both the wavelength is same. So that means, suppose if A is equal to B, তার মানে 1 by A is equal to 1 by B. If A is equal to B, then 1 by A is also equal to 1 by B. So let us write it. So 1 by lambda of helium plus, that is equal to 1 by lambda of H. So now simply put down both the values. What is lambda of helium plus? This is basically 4R into 1 by 4 minus 1 by N2 square. And what is 1 by lambda H? This part we got it as 3R by 4. 3R by 4. So do not put down the values of R over here, because ultimately they will cancel out. So what we get is the 1 by 4 minus 1 by N2 square, that is equal to, this 4 will come to the right hand side, that is equal to 3 by 16, equal to 3 by 16. So that means from here I can write that 1 by N2 square, 1 by N2 square, that is equal to 1 by 4 minus 3 by 16. So that is equal to what? 3 by 16 যদি করা যায়, so we will get it as 1 by 16. So 16 just in a 1 by 16 will be the answer. So do the calculation, you will get it as 1 by 16. So that means 1 by N2 square is equal to 1 by 16. That means what? Therefore, N2 is equal to 4.
4.
So that means transition, they have asked us the transition. The transition will be 2 to 4. This will be the answer. So is the numerical clear to you? Yes or no?
Yes, sir.
Yes, sir.
This is it. So it's basically two sums and then equating them. Formula is same. The simple mathematics, simple equation solving sum. These are. So then this is the topic of your atomic spectrum. Is the topic clear to both of you?
Yes, sir.
Everything that was
Yes,
taught.
sir.
So now let's move on to the drawback of Bohr's theory. The drawbacks of Bohr's theory. Did we do it before? Oh no, we did it only. Drawbacks of Bohr's theory was done. Then we will do. Since you have done the drawback of Bohr's theory, that's right. Now we are going to see the de Broglie equation. The de Broglie equation. So from now onwards, we are actually going to see a bit of quantum physics. So now we are going to enter the field of quantum physics. Although quantum physics is not there in our syllabus because you do not know any of the mathematics regarding quantum physics, taught mainly in the BSc level of physics or chemistry. Here we'll be just touching the yes, wave mechanical model of atom. This is called the de Broglie equation. This D is in small letter, not capital letter. So his full name is Louis de Broglie. The Louis is not written, only de Broglie is the de Broglie equation. So yeah. So that means say till now we have seen one thing, that light. We have learned about light, and what did we see is that light has actually dual nature. That is, sometimes light can behave like a wave, the wave nature of light, where we learned about waveform, electromagnetic waves, all those things that we have learned. That means the electromagnetic spectra. Electromagnetic spectrum. That means light is a wave. Light is behaving like a wave. Electromagnetic spectrum. Again, in Planck's theory that we had learned, class 11 only, few days back, there actually we had said that light is being emitted in the form of small packets. So that means there so we are actually considering light to be a particle. So in electromagnetic spectrum, we considered light to be as wave, whereas in Planck's theory, light was considered to be a particle. That means this is the Planck's quantum theory. Planck's quantum theory. So in Planck's quantum theory, we saw that light behaves as a particle. Whereas while learning about electromagnetic spectra, there we learn that light is behaving like a wave.
Electromagnetic spectrum.
Yes, electromagnetic spectra, it is behaving like a wave. So that means light can basically behave both as a wave as well as a particle. So light can behave both as wave as well as particle. So both the properties of wave as well as particle is present in the light. And what is actually light? Light is basically made up of photons. Photon is the constituent of light. So basically this subatomic particle photon can have both wave nature as well as particle nature. Both of these. There is no such on-off switch, so is not there. There is no switch inside this photon, which is basically directing it that now you will behave as a wave, or if the switch is off, now you behave as a particle. There is no such mechanism. There is no one who instruct that photon when to behave as a wave or when to behave as a particle. So that means both the wave and the particle nature is actually existing simultaneously. So this photon particle can behave both as a wave and as a particle, and both of this nature is existing simultaneously. And you will be seeing the proofs also. See, when you have done the reflection, refraction, all those things. By the way, you'll be reading this chapter also. See, most of the things that we are studying under this chapter, most of it again you will read it in physics in class 12 in modern physics. All the numericals on Rydberg equation is also there. Then this chapter is there. So all of this in physics also. But ultimately it's more of physics and less of chemistry. So yes. So yes, you have learned about reflection, refraction, all those things that you did. Over there, light was considered to be a particle. A particle is coming, striking, getting reflected back like. So when you learned about reflection, refraction, their light behaved as a particle. But if you see diffraction or interference, in those cases, light is actually behaving like a wave. Both the nature exist simultaneously. So the logic of de Broglie was that if light being a subatomic particle can exist both in the wave form as well as an particle form, then electron, which is also a subatomic particle, then this can also exist in that manner. Electron can also behave as a particle and also as a wave simultaneously, because ultimately this is also a subatomic particle. So electron can also behave as a wave as well as a particle. So till now we had been saying electron to be a particle, but now he is saying that no, electron can behave both as a particle and as a wave simultaneously. Okay, so that means we can write over here that both the particle as well as the wave nature exist simultaneously. Both particles, both particle, both particle and wave nature exist simultaneously in subatomic particles. What are these subatomic particles? These are like electrons, photons in this. But the thing is, it is not like this that he probably will say and everyone will accept. The story is not like that. He has to prove it. So obviously, people will ask that fine, if it is a wave, then what is the wavelength of that wave? How do I calculate the wavelength? How do you find out the wavelength? How to measure the wavelength? Immediately, the scientist, the other scientist will ask this question. So that means it's not like he will just say something and people will accept it. So he needs to give formulas in order to calculate the wavelength. So that he did also. So let's see the derivation. It's a very simple derivation. Let's suppose you have two equations for energy. One is E is equal to mc square. You have obviously heard about this equation. E is equal to mc square. The very, very famous theory. This is the theory of relativity. Einstein's equation. Calculate energy. And again, in this chapter only you have learned E is equal to h nu, which is our Planck's equation. Planck's equation. So what did de Broglie do is he equated both these equations. So that means mc square is equal to h, and ah nu can be written as hc by lambda. Nu can be written as c by lambda. So that means c and c cancels out from both sides. On this side you have only one c. So you get mc is equal to h by lambda. Therefore, lambda is equal to h by mc. Now the thing is, everything so does not move with the speed of light. Nothing moves with the speed of light. It moves with a different velocity. It has replaced this c with a velocity v, h by mv. So the de Broglie, the equation that he gave to calculate the wavelength is the wavelength is calculated by this formula h by m, where h is the Planck's constant, h is the Planck's constant, and mv the momentum. Mv is the momentum. So this equation is called the de Broglie equation. De Broglie called de de Broglie equation. Very simple formula. Lambda is equal to h by mv. And this lambda, since he made the equation, that is why this is known as the de Broglie wavelength. De Broglie wavelength. Okay, so that's it. So the thing is that people ask that, okay, you are telling that it can behave both as a particle and as a wave. Then how are you going to calculate that particular wavelength? So that is why de Broglie gave a formula to calculate the wavelength of this subatomic particle. And that formula is lambda is equal to h by mv. So is it clear to both of you? Is the derivation and the de Broglie equation clear to both of you? Hello? Hello? Hello?